Let's take a look at another example. So in this case, we're actually given the expression for our electric flux density, D is equal to Z rho cosine squared of phi in our Z direction with units of coulombs per square meter. And we want to calculate in part A the charge density at some particular point, 1 pi force 3. And in part B, we want to calculate the charge enclosed by some cylinder, which is centered on the Z-axis with radius of 1 meter and top at 2 meters, bottom at -2 meters. Okay, so for part A, what we're going to be doing is we're actually just going to be using Maxwell's first equation. So if we want the volume charge density and we have an expression for our electric flux density, we can just say that rho v equals the divergence of our electric flux density. So in this case, because we only have a z component, it works out to be pretty easy. So we can tell that this is also in cylindrical coordinates because we have our rho and phi dependence. So this is going to be the partial of our z component with respect to z. So just from our definition of divergence. So we get that this is rho cosine squared of phi coulombs per cubic meter. So it's coulombs per cubic meter now because we're looking at a volume charge density. So our point above, of course, here we have, this is our rho value, our phi value, and our z value. So plugging those in, we see that our rho v is just going to be equal to 1 cosine squared, and we have our pi force, and this comes out to be 0.5 coulombs per cubic meter. So this would be our answer for part A. So this is our charge density at this one particular point. All right. So for part B, we're going to be back to doing our integrals. And so what we could do is we could integrate a rho v equation. So we have this rho v equation here. So we could integrate over the volume. And so this is what we said, sort of our general form. We said that our charge is equal to the integral over the volume of rho v dv. But of course, we're talking about Gauss's law, so let's get some practice with that. So we said this is also equal to the integral over the closed surface of d dot ds. So we can do either of these. In this case, let's go ahead and get some more practice with this method. So using our Gauss's law for B then, we can say that our Q enclosed is going to equal, of course, our overall flux out of that volume. And so we can write that as the integral over the closed surface of d dot ds as I have above. And so now we have a cylinder, which we've encountered that once before when we were looking at the Gaussian surface for our infinite line charge. And so we said we have flux out of the sides as well as out of the top and the bottom. So we're going to have three parts to our integral. So we're going to have the integral over the top plus the integral over the bottom. So all of these are surface integrals. I'm just writing it with one integral just for ease of writing it. Plus the integral over the sides, and each one of those is going to be evaluated at d dot ds. Okay, so let's sort of simplify a little bit before we move on. So we know that on the sides, our d is going to be tangential to ds. So d, which is only in the z direction, so coming back up here, we see our d is only in the z direction. So that's going to be tangential to our ds, which is in the phi direction. Okay, and so what that means is those terms are going to go away. We're going to have basically d dot ds, we're going to have a unit vector in z dot unit vector in rho, which is going to be equal to 0. So we can ignore our term for the sides. Okay, so now another consideration is that we notice that our cylinder is going from -2 to 2 for our z range. And so what we can say is because they're equidistant from the origin and our equation here is dependent on z, which again is sort of measured from our origin, or our xy plane would be more accurate, we can say that our top and bottom portions of our cylinder are equidistant from the origin. So top and bottom equidistant from origin. Basically what I was trying to say, and I think failing to do so, is that the magnitude of our d is going to be the same. So at both of those, we're going to have the magnitude of z the same based on this equation, which has the dependence on z as shown here. So let's consider sort of the two cases. So at the top, we're going to have our d dot ds, where our ds out the top is going to be in the positive z direction. So we're going to get something that looks like this. So d dot rho d phi d rho in our z direction. And on the bottom, we're going to have d dot ds equals to d dot rho d phi. So the same sort of magnitude there, but this is now going to be in the negative. So we're going to be going in the negative z direction. So we have negative u of z. Okay, so at first glance, you might say, oh, well, that's kind of nice. They're going to cancel out. But, of course, we need to remember at this point, we're going to be evaluating at z equals 2. And at this point, we're going to be evaluating at z equals negative 2. And so again, because we have this z term in our d equation, essentially what we'll get is that this negative sign here is going to cancel out with this negative sign. And we're going to get that we have the same flux at both, the same electric flux at our bottom and top surfaces. So we can say the flux on the top is equal to the flux on the bottom. So what we can say then is, sort of coming back to this expression, we can say because we have the flux, or the integral of the top, the integral of the bottom, which when we include this ds as well, that's our flux on the top and the flux on the bottom. So we can say that our overall flux for the cylinder is just going to be twice the flux out the top. And so we could have easily said that's equal to twice the flux out the bottom as well. Of course, both are the same thing. So we've sort of simplified what we had to integrate here. So now coming back, we can say our charge enclosed is, of course, still the overall flux. We said that overall flux is twice the flux out of the top because we have 0 out the sides and the same flux in the top and the bottom. And so this is then going to equal to the 2 times the integral over the top of d dot ds. All right, so now for our actual integral, we have that 2 out front. Our rho is going from 0 to 1. Our phi is going from 0 to 2 pi. So of course our z is varying. Our z is fixed at our top. So we're going to have z times rho cosine squared of phi. So this was our d equation, and that's in the z direction. And then from our ds, we have rho d phi d rho. And as I said, this is going to be evaluated for z equals 2 because we're on that top surface. All right, so just evaluating that, we get 4. So our z, which is 2, comes out to multiply with the 2. Integral from rho equals 0 to 1, and we can actually just separate now. So we have rho squared d rho, and the integral from phi equals 0 to 2 pi of cosine squared of phi, d phi. So the rho is pretty easy to integrate, so we just get 4 out front still, and that becomes 1/3. For our phi integral, what we can do is we can use a trig term to make this a little bit easier, a trig identity. So we can say cosine squared is 1/2 the quantity of 1 plus cosine of 2 phi, d phi. And so now that becomes a little easier, so we can say this is 2/3, so bringing this 1/2 out as well. So we get 2/3 times phi plus 1/2 sine of 2 phi, and that's evaluated from 0 to 2 pi. And of course, sine for an even number of pi is going to be 0, and at 0, it's 0, so this term goes away. And we're just left with 2 pi from that first term. So we get 2/3 times 2 pi, and that's going to be our Q enclosed. So 4 pi over 3, and our units on that are going to be coulombs because our rho and z distances were in meters. So if you want for practice, what you could do is you could go back and you could evaluate this integral just to verify that Gauss's law is true, and we get the same Q enclosed regardless of which of those two integrals we evaluate.